Good day, friends. Today we're going to talk about something called polarization. This would be today's our topic, and this term might be a little bit unfamiliar to you. However, it's not something very complex, in fact, because it is in some sense continuation of the wave optics, because it has something to do with wave nature of light. Okay, so what is polarization by its definition? In simple terms, it is making the light waves vibrate in one direction instead of many random directions. Okay, for now it would be a little bit complex, but we would come to this a little bit later. Okay, so let's start from the basics. Last time we have discussed for a long period that light is electromagnetic wave, right? It is the disturbance in electric and magnetic fields. Okay, for example, in this diagram, yeah, we see here magnetic field which oscillates vertically, and you can see it oscillates in z direction like this. Yeah, and also we have electric field which oscillates horizontally in y direction, as you can see it just right here. But please remember that it doesn't have to be this way all the time. In fact, electric field can be oscillating vertically, it can be oscillating in some angle. The same thing goes for magnetic field. It does not have to oscillate vertically, it can oscillate horizontally also in some angle, and so on. But we need to remember that these two have to be perpendicular. At any case, this is the rule coming from their nature. Okay, and we can see that wave itself travels in x direction, that light travels here. Okay, good. If you understand it, it's already the good start. Okay, so let's look at electromagnetic wave equation. So basically, if we know that is a wave, then there is some equation which describes its wave nature. Yeah, it might look to you a little bit complex, but in fact it is not. Why? Because it is exactly what the simple oscillation equation is. Yeah, do you remember this? X equals amplitude cosine omega t, and so on and so on and so on. The very same thing goes for oscillating electric field, oscillating magnetic field, and you can see here that the relation between electric field and magnetic field is just the speed of light. Yeah, if I move it here, I have to move speed of light here. So you have something like C equals electric field divided by magnetic field. Okay, we need to remember this thing because it will be useful to us a little bit later. Okay, good. Okay, let's talk about pointing vector. Pointing vector, yeah, this is indicated by letter S. Yeah, this is pointing vector. So this is something which shows the direction. This is the vector which shows the direction of energy spread. Yeah, because we know that electromagnetic field it oscillates like this, but as we have said before, light itself moves this kind of direction, and that is exactly our pointing vector. It is if we say that light is electromagnetic radiation. Yeah, do you remember that? I hope that you remember that. Radiation is the spread of energy. Basically, it's not something hard. And we need to remember, yeah, this is cross product. They have to be perpendicular to each other. This is really important. Those two fields, those two oscillating fields have to be perpendicular, and they must be divided by permeability of the free space. Yep, and that gives us direction of pointing vector where that energy of light is spreading. Okay, good. If you understand it till this time, it's already a very, very good start. Okay, let's go. So how does light truly look like? It's a little bit complex thing, in fact, because before, for example, here, you can imagine it. For example, if you look at that light, for example, this is your eye, and if you look at it, it would look to you like it is oscillating vertically and horizontally. They have 90 degrees like this. But in fact, it is not something like this. It is drawn like this just for simplicity. Yeah, this one is wrong. This one is wrong. What is real is this one. Yeah, this thing might look a little bit complex to you, but in fact it is not. Why? Because look at these violet lines. All of those violet lines are magnetic fields, and all of those blue lines are electric fields. Yeah, and what I want to show by this, I want to show that, for example, if this is magnetic field, for example, let's forget about all of these. We're not interested in those. For example, we have these magnetic fields, and if this is a magnetic field, yeah, then its electric field looks totally 90 degrees like this. This is electric field. Okay, and just the same way, we have many electric fields, magnetic fields, inside of each other. Yeah, it is also here we have some magnetic field, for example, and perpendicular to that, which is this one is its electric field, because here you can see it is also 90 degrees. It's still there. Yeah, and inside of itself also there is a magnetic field and electric field, and so on and so on and so on. So what I want to say by this picture is that many electromagnetic waves are inside of each other. It's not just like this. It is also like this. We have electric and magnetic fields here. Yeah, both of those are vectors, and also it can be also like this. This is also electric magnetic fields. Yeah, this kind of, and so on and so on and so on. There are many oscillations in electric and magnetic fields. Okay, this is the correct version. If you cannot imagine it to yourself, then look at this image. This is a really good image, which is drawn in 3D, and right now I hope you understand that all of these, concentrate on these, not on this yet. We're going to come to this very slowly, okay? So a polarized wave, which means that, as we have already said, polarization is making light in one direction. As you can see it's one direction, only vertical. But here it is many directions, like this one, Here we have many directions, and we will assume that all of those oscillations are in all 360 degrees, Okay, we'll just assume that, But it still works, in fact. It works pretty good. And we concentrate on this. So our aim for today, to understand how we get from this one to this one. Okay, this is polarized. You can see it is many directions, and then it goes to just one direction. And that is exactly what polarization is, but we need to understand it not just from the picture, but also from mathematical perspective. Okay, good. Okay, let's concentrate on this one. What is this? Is that, as you can see here, we have many directions, but please note that I write here only electric fields. There is no magnetic field here, And it is strange. I have said that, well, if all of these are electric fields, then, for example, to this line, it must be perpendicular in 90 degrees, this one. And also for electric field, which is here, it must be like this, magnetic field, right? It must be. Well, I will tell you why, but let's wait a little bit, okay? So you can see here many directions of electric fields, then they become just one direction of electric field, So as you can see, after passing this thing, which I will tell you what it is, it will be traveling just in one direction. So it is, if you cannot understand what these lines are, in fact, these are waves, Oops. Like this, You just imagine it like this, or it can be something like this. So the main principle is that wave is traveling vertically, only vertically. Here it was traveling in all directions, but after passing this thing, it became just in one direction, okay? But it doesn't have to be all the time just vertical. It can be at any angle. It depends on this thing, the name of which I will tell you just in 2 minutes, okay? The very same principle here, many directions of electric field, only electric field, remember this. And after passing this thing, which is horizontal now, only horizontal lines can pass through. But remember, if you ask again, what are these lines? This is the direction where the electric field is oscillating right now. It might be oscillating like this. It can be oscillating like this. Okay, good. If you can imagine it, I'm happy. Okay, let's talk about this. First of all, we had two problems. The problem number one, why only electric field? The problem two, what is this thing? What is this thing that makes light pass only in one direction? Okay, let's go here. Why only electric fields but not magnetic fields? In fact, electric fields interacts with electrons in the atoms. We know that everything consists of atoms. And every atom has electrons. That's why electric fields, which is approaching them, the electric part of electromagnetic wave, they interact with electrons. That's why we draw their electric fields. What about the magnetic field? What is the problem with magnetic field? Well, magnetic field, it interacts with electron in atoms very weak. It interacts. It is not zero interaction. There is an interaction, but it is very weak, so it is negligible compared to electric field. Okay, so that's the very reason why we don't apply here magnetic field, because it is negligible. It is there. It does not disappear. In fact, inside of this image, there are also magnetic fields like this, like this, like this. So each one of them are perpendicular, and so on. It looks like this. In fact, magnetic fields are also inside of electric fields. However, as you can see here, they are very weak. Interaction, and it is negligible compared to electric field, that it is not even noticeable. Okay, that's the answer for the first question. What is the answer for the second question? What are those yellow things? In fact, it is not something yellow. I just draw it in this color, so it was better visible. So, okay, it is here. This is here. Okay, polarizers vs Polaroids. Versus. These things are called Polaroids. But this thing is also called polarizer, in fact. But let's understand their distinction. Why this thing is also called Polaroid and polarizer. But this thing, for example, this glasses can be considered as polarizers, but not Polaroids. This thing cannot be considered as Polaroid. Okay, polarizer is the general name for everything what can polarize. So if we have anything, it might be, for example, the screen of our smartphone. It can be polarizing glasses, polarizing anything what can polarize can be considered as a polarizer, okay? But Polaroid, it's exactly something made of a plastic or these special polymer discs which can polarize, So that's why Polaroids is just one of the things what can polarize. That's why it's just one of the group of polarizers. But not all of the polarizers will be Polaroids, because Polaroids, by their definition, it's just a plastic polymer discs just we use for experiments, okay? It's a tool, better to say that, okay? Okay. However, what are polarizers and analyzers? I understand right now it's a little bit problematic. Let's understand for here, let's remember it as rows. So polarizer and analyzer, okay. What are those things? For example, again, many directions of electric field oscillating, they pass this Polaroid at an angle. Yeah, this is Polaroid. It is also polarizer because it can polarize, but this is our plastic polymer disc, which we use just for experiments. Yeah, that's why it's a tool. It's a Polaroid, and exactly at the same direction of its lines. Yeah, of its lines, electric fields continue to oscillate, and then it comes out like this again after second one. Yeah, we can put here many Polaroids. It can be here, it can be here, it can be here, and so on and so on and so on at many different angles. Okay, the first Polaroid is called polarizer. Yeah, it's a roll of it. It will polarize. But the second, third, fourth, and so on and so on and so on, any next one is called analyzer. Yeah. And why is this important? I will keep it as a secret till the end. That's why please listen to me carefully. Okay. Let's talk about intensity of light and electric fields, because today's topic will be mostly dependent on intensity of light. Yeah. Okay. So we have such kind of formula. Intensity of light equals 1 divided by 2, which is the half speed of light, permittivity of free space of electric field, yeah, and electric field squared, yeah. Okay, good. So what we get from this thing? Well, in fact, this is constant. This thing is constant as well. This is just a constant number. Only thing that we need here, we can see that intensity of light is positively proportional to its electric field. Yeah, you can see it here. Intensity and electric field, they're positively, they have positive correlation. Yeah. Okay, let's prove that formula. First, let's prove that formula. This is the very fundamental formula, which is Poynting vector by its nature. Yeah. Okay. Let's put inside of the magnetic field. Its formula, which is this one. Yeah. We have already shown it at the very beginning, if you remember it. Okay. The relationship between electric field and magnetic field, it's the speed of light. We have already said that. If we put it here, then you can see that we have one more electric field, and one electric field is here, and then we will have electric field squared. Below, we will still keep permeability and speed of light. Yeah. So we have this kind of formula. Okay. Also, we have one more formula, which is this one. 1 divided by mu 0 C equals C E 0. So mu 0 is permeability, E is permittivity of free spaces. Okay? So basically, it's the very same thing as this one, but for their constants, because mu is the constant for magnetic field, and E is the constant for electric field. Yeah, it shows how much the space allows electric and magnetic fields. That's why it's both of them come from the same origin. Okay? Okay. So if we change this mu c into ce, then we would have something like this. Okay, something very familiar. Right now we're very close to that thing. Yeah, intensity is positively correlates with electric field squared. Yeah. Okay, we're very close to that. But yet we don't have here 1 divided by 2. Okay, 1 divided by 2. We have this formula of the electric field oscillation. Yeah, electric field wave. Okay, if we put square from both sides, all of those things will be squared, as you can see it here, here, here. Okay, if we put this value, yeah, if the electric field squared is equal to initial electric field squared cosine squared omega t, then we can put it here, right? And then you'd have something like this. Yeah, we just put it inside of that. Okay. Okay. Yeah. Good. We know that intensity, it's an average time Poynting vector. So what did we say about a Poynting vector? Poynting vector is the direction and the measure of the energy spread. Okay, but that energy in average time is exactly what our intensity is, right? So cosine omega t would be equal to 1 divided by 2. Why? Because the average time in maths we use root mean square. Yeah, not for average time, but average anything average we use root mean square. Yeah, it is 1 divided by square root 2. You can read about this. Why do we use all the time root mean square? But I wouldn't waste time on that. You just should look at yourself. Yeah. Okay. And if we apply it here, yeah, if cosine omega t itself is this root mean square, then its square, it's 1 square and square root 2 squared, and that's why how we get rid of that square root. Yeah. Okay. Good. And then if we paste it, yeah, if we paste this thing inside of this thing, then we exactly get how intensity is positively. Has positive correlation with electric field squared. Yeah, that was a proof of that formula. And right now, finally, we reach our main topic, the main law. This law is called Malthus's law. Okay, so what does it do? Yeah. Okay, yeah. One thing that I forgot to explain before we move to the Malthus law, let's talk about this one. Yeah, let's talk about this one. Okay, look at this. We have said that these Polaroids can be at any angle, right? let's consider different kind of situations. This is case 1, this is case 2, this is case 3, this is case 4. It is not many Polaroids standing one after another. No, they are independent situations. It's situation number 1, situation number 2, situation number 3, situation number 4. These are 4 independent situations, only with one Polaroid. Okay, what's the problem about this one? The problem is not the angle of the Polaroid, because you can see that all of the Polaroids are in the same angle. They all look vertical, right? However, what's the problem? What's the problem? The problem is the angle of the incoming electric field. Yeah, electric field here can pass for 100%, as you can see. Yeah, it's like a person trying to pass through from this lines. Yeah, so this tiny, thin person can pass through it. Yeah, what if the person tries to move like this? Well, basically in real life he cannot, because if we try to move some stick through this kind of slits, let's say, we cannot. In fact, it would be problematic. But in physics, we will divide it into components like this one, and these ones cannot pass through totally. You can see it; it's definitely logical. But this component of this original electric field can pass. Yeah, this component can pass. So it is important to draw alpha here, the relative angle between the main axis and the incoming electric field. Okay, good. The very same thing goes here. For example, here, let's say it's small angle like 30 degrees. It means that most of the light can pass through, some of it cannot pass through. Here we have totally negative situation where most of the light it cannot pass through, but here it does pass through. Okay, some of it, just not the most of it, but some of it. And the relative angle between them would be this one. It would be very large. It's 60 degrees, and we will need this angle a little bit later. Okay, in this case it would not pass through at all. It's the same thing like you are trying to move some of your object through this kind of slits. It will not pass through logically. Okay. After passing Polaroids, electric fields lose components, right? Okay, I hope you understand it. I have explained it here, and you must remember this as some certain rule, okay? What about this one? At any angle, it does not matter. First Polaroid cancels half of the electric fields. Okay, it does not matter which angle we put our Polaroid. It can be like this, it can be this kind of angle. It does not matter even if it's horizontal totally. Any angle of the Polaroid, any angle, will not let light, half of the incoming light pass through. Okay, it will always be 50%. Okay, the question is why? Because if we consider each of those lines separately, this line can pass through for 100%, right? This one cannot pass through at all. It will not pass through 100%. The 45 degrees, will pass in half, the other half will not pass. This one will pass in mostly, will be cancelled. Some of it's a little bit, these components can pass through. About these ones, they mostly can pass through, and so on and so on and so on. In fact, here we have many other lines of electric fields, and each one of them have horizontal and vertical axes, and one of the axes of course will be cancelled totally, and that's it. Because half of them have their components. Well, all of them have their components, and half of all of these lines are horizontal, half of them are vertical. That's how we get rid of half of it anyway. Okay, interesting. That's a little bit kind of interesting. You should remember this one. Intensity 1 equals half of the initial intensity 0. Okay, good. Let's head back to the Malloy's law. So look at this one. As I have said before, we have many directions like this one. It is 100% at the very beginning. After passing through polarizer, it will be 50% anyway, as I have said. The first one is polarizer, the second one is analyzer. Okay, what's the problem with analyzer? It will, this thing will analyze. What should it do? And it thinks, should it let any of the light through it or not? In this case, the polarizer will not make any analysis. It will just cut half of it. That's why it is just polarizing. And this thing is analyzing. It is not logically thinking, of course. It is not a logical analysis, but it's just a division into components and which component it does not let through. And that is called analyzing. Of course. This thing has some components, and only those components which align with this axis, of course, those ones will pass through, but other half will not pass through. Okay, good. Okay, in terms of mathematical formula, what does it look like? We have already said that intensity is positively correlated with electric field squared. Initial intensity is also positively correlated with initial electric field that is incoming. We have this formula for electric field oscillation. Then if this is true, then this is true, right? Because we just put squared from both sides. Here we have squares, here we have squares. Okay. If we try to find the relationship between these, right? The relationship between these, which was here, you can see it. Instead of the electric field itself, we can put this formula, or better to say this formula, because here we have squared electric field and it is here. We can open up with this formula And you can see here that at the above we have electric field 0 squared, cosine squared alpha, and below we have electric field squared 0. And that's why we can cancel those two out. And here at the above we have only cosine squared alpha. And here we still have our intensity, so our formula would look like this. This is the Malus law formula. This is really important. Okay, the intensity of the light which is passing through after some analyzer will be the initial intensity and multiplied by cosine relative angle between those two. Yeah, cosine squared. Yeah, please don't forget about square. Okay, what is this graph? This is the polarizer axis. For example, we have here polarizer and have many this kind of slits. Yeah, then this is our polarizer axis. Okay. What about this one? What is this one? Well, it is the second polarizer. Yeah, this is the second Polaroid, which stands here, and then the second Polaroid after it looks like this. So this is the angle between first Polaroid, which is this one, and the second Polaroid, which looks like this one. So we need to take that relative angle between those two, and then we can see that if we have some incoming light, right? Yeah. For example, the first polarizer let lights through like this, straight. Yeah. Then when it was coming here, it divided into components. One of the components is like this. For example, light was coming here, and then it divided into components like this component and this component. Those two are 90 degrees. But this component cannot pass through because Polaroid itself looks like this. Yep, only this axis can pass through. That's why this is green and this one is red. It does not pass through, and this one passes through. Okay, good. Okay, let's try to solve problems so you understand it better. Okay, here we have something like this. Let's try to understand this problem. Yeah, there is no any words, but only the image. So you see here first Polaroid, the second Polaroid, third Polaroid, and the fourth Polaroid. The first one is obviously it is polarizer. The second one is analyzer. Third, fourth are analyzers. Yeah, because they think should they let any light through. Yeah. And let's learn how to use this formula. After passing the first Polaroid, of course, this would be different intensity because intensity would decrease. This one would be intensity 1, this thing would be intensity 2, this would be intensity 3, and at the end we have intensity 4, and we need to find this intensity 4. Okay? Okay. Of their angles, as you can see, this is 0 degrees. It is tilted to 0 degrees, it is tilted into 30 degrees, 60 degrees, and at the end it is 90 degrees. However, one thing that you need to note, in this formula, in this I equals I0 cosine squared alpha, each time, you need to take this as not their angles that they are tilted, but their relative angles between the incoming and the out intensity. Yeah. So for example, for the first one, I hope you remember, it is exactly the half. We use, where is it? Did I write? I hope I did. Yeah, this one. Yeah. Okay, look at this one. This thing would be important to us. Intensity 1 will always be the half of intensity 0 at any angle. We have already discussed it. Yeah. So I don't need to waste any time to prove it. It is intensity 1 equals intensity 0 multiplied 1 divided by 2. So our intensity 0, for example, let's say it's for convenience, this would be 100 watts divided by meter squared. Yeah. Okay. Intensity is like that. Okay. Yeah. Good. And then if our initial intensity is 100, then definitely it would be what? This thing is 50, right? If you ask me why, then oops, what is going on? Yeah, this is 100 multiplied 1 divided by 2. This would be 50 watts divided by meter squared. Okay, good. What about the next ones? Well, we can see that their relative angle is 30 degrees. But the next time, it's again 30 degrees. And again, here it is 30 degrees. Okay, then we see here the same tendency, very interesting tendency. We have here intensity 2, which is equal to intensity 1. And we apply this formula of the Malus law. It would be what? Here we have cosine squared, and the relative angle is 30 degrees. Yeah, we don't take it because it is 30 degrees. We take it because the relative angle is 30 degrees between the first one and the second one, right? Yeah. That's why here this thing would be intensity 2. Intensity 1 is already 50, and cosine squared of 30, it's the same thing as cosine 30 cosine 30 multiplied cosine 30 again. And that's why this thing would be 50. 50. Cosine 30 is square root 3 divided by 2. Here we have again square root 3 divided by 2. Well, here this thing would be 50. Below we have 4. Above we have just 3. Square root 3 multiplied square root 3 gives us just 3 itself. Yeah. So above we have 150, and below it would be 4. If we cancel it, yeah, we would have something like what would it be? It would be something like 37.5. Is it so? 37.5 watts per meter squared. Okay. So for I3, it would be the very same formula. Yeah, right now we would write something like I3 equals I2. Why? Because the initial intensity for I3 would be this one, not the very beginning, but it would be the next case, in fact. Yeah, we are not concentrated on this one, we're not concentrated on this one, because each of those cases are different situations, in fact. And right now, we are interested in this moment, right? That's why the initial intensity for that I3 would be I2. And then we would apply here cosine squared relative alpha. Yeah, well, if it was 60, if it was 30, their relative alpha between each other is 30 as well, right? So it's not about, we don't write here 60 because intensity 3 is about 60. No, after passing through, for example, light already comes here like in this angle. That's why when it will break into components, it would be something like, it would break into this kind of components and this kind of components. And these components would be totally destroyed, they would not pass through, but these components would pass through exactly. Yeah, that's why we need to take this relative angle, this alpha. Okay, this relative alpha. Okay, good. So this relative alpha for us would be 30 degrees because it already approaches us in 30 degrees, and this relative this axis of the Polaroid is 60 and their relative alpha is 30 between each other. We already know what's the meaning behind cosine squared 30. It's 3 divided by 4. We have already done that. This thing has to be 37.5 multiplied 3 divided by 4, right? Okay, let me calculate it fast. So basically it is 125 watts per meter squared. Okay, and the last thing that we need to calculate is the I intensity is I4, intensity 4. It is intensity 4. Its initial intensity is intensity 3, and cosine squared relative alpha between those two would be again 30, not 90. Don't write 90 because it is relative angle between those two. Light already approaches this last one with this kind of angle 60, and this angle is 90. We need to take their relative angle, which is this one. We need to take this alpha. Okay, that's why their relative angle would be 30. Each time, after passing each Polaroid, those electric fields just lose some of their components, okay? It would be again 30, and then this thing would be 28,125 multiplied 3 divided by 4. 21, well, about 21 watts per meter squared. Okay, this would be our answer for intensity 4, for last intensity. It must come out in the form of 21 watts per meter squared. That is our answer. So if we have 4 Polaroids, each of the next Polaroid tilted to 30 degrees relative to the previous one, then the last intensity would be 21 watts per meter squared. Okay. Now let's move to the next one, the problem number 2. Okay, right now I will teach you one principle. We have already solved this problem number 1 in details, but right now it's a little bit complex problem compared to the previous one. It's not hard, but it's a little bit, just a bit complex than the previous one. So here we have many Polaroids. It's not just 4, yeah? And I would put here some numbers like this. It's not even numbers, it's just dots showing that there are many of them, okay? So here we have Polaroid number 1, then Polaroid number 2, Polaroid number 3, 4, 5, 6, and so on. There are many Polaroids between them, okay? Each one of them is tilted to 1 degrees compared to the previous one, okay? Compared to the previous one. And then what you would see that here we have 90 Polaroids, yeah, because the last one is tilted to 90 degrees, okay? So we have some incoming intensity 0, then it passes 90 times, yeah? This one would be intensity 90, this last one would be intensity 91. Okay, so what should we do here? Should we calculate something like this from the very beginning to the very end? Well, that would be a little bit kind of problematic, don't you think? So instead of that, I would do something like this. Yeah, we definitely know that intensity number 1 is just half of intensity 0, right? This is 1 divided by 2, okay. But any next one, it would look something like this. Intensity 2 is intensity 1 cosine squared alpha, yeah? We know that relative angle is 1 degrees during all the Polaroids, okay? Let's write for here, yeah? Intensity 2 cosine squared alpha. This would be cosine 4, intensity 3 cosine squared alpha. Okay, do you see the tendency? So it shows us what? If I take this thing and put it here, well, you can see that this thing would be what? This thing would become intensity 1 cosine squared, but here we have already squared, then it would be what? Cosine 4 power alpha. Okay, if I take this, if this says intensity 3, I can put it here. I could put this thing, but I can put also this thing. Okay, so what it shows is that this thing would be what? this thing, if I put here intensity, instead of intensity 3, I would put this value, intensity, then it would be intensity 1, cosine full power, cosine squared again, this thing would be cosine 6 powered alpha, right? Okay, and it goes on all the time, as you can see. So, which means that by this tendency, the last one, intensity number 91, must be intensity number 90 cosine squared alpha. Okay, cosine squared alpha. But the problem about it, if we do it by this tendency all the time, then we can see that in the last, if intensity, instead of intensity 3, we put here intensity 1 and cosine 6th degree, it's just, if it's third one, you put here 6 and so on, then it would be twice as much, then it would be what? It would be cosine, if I continued, it would be intensity 1 cosine 180 power alpha. Okay, 180 power alpha. And that would be a little bit problematic. Well, I know the meaning of intensity 1. I can put it here, and then we would have our answer. So it would be intensity number 91, would be intensity 0 in a half, and cosine 180. Here we have 1 degrees. Okay. Okay, so this thing would be intensity 0 multiplied 1 divided by 2 is just 0.5. We definitely know that. And also cosine 180 power 1 degrees. This thing would be 0.90 7 and 3, like this. Well, okay, what does it mean? If I calculate it and multiply by 0.5, then this thing must give us intensity 0 multiplied 0.48, I'm sorry, this thing would be 0.486, something like this, and so on and so on and so on. So what does it mean? It means that in terms of percentage, if I turned it into percentage, then this thing would be what? It would be that intensity 0 is some value that we don't know, but we know that compared to the very beginning, we're not given intensity 0, but it does not matter. The important part is that after putting 90 polarizers, we think that this thing must not pass any light through because there are many of them. However, this is a little bit kind of paradox. Instead, it gives us a little bit less than half of it. Do you understand? So after first polarizer, after first one, it lost 50%. So here, if it was 100%, then here it is 50% already. But here it is 48.6%. It is not 48 and 6% compared to the previous one, compared to this one. It is, as you can see in the formula, 48.6% compared to the intensity in the very beginning, which means that after first polarizer, it loses half of the intensity. But after passing all these polarizers, it loses just 1.4% of intensity. Do you get it? So it's a little bit interesting thing. As you can see here, it's just 4 polarizers, but it is 21 watts per meter squared. But here you can see that, and 21 is definitely, if the beginning is 100, after passing 4 polarizers with relative angle of 30, then it's just even less than 4 times, well, or better to say, it decreased about 5 times, But here, as you can see, after first polarizer, if we put 90 polarizers, and after first polarizer, it decreases by half, but after 90th, it decreases just by 1.4%. And that is very interesting to do. Okay. The last thing that we're gonna study about polarization for today is the Brewster's law. Okay. Brewster's law is something very interesting. For example, if we have something polarized light like this, okay, what is this green points? You know that yellow lines like this one, you already know what it is. We have worked with this all this video. But what about these green dots? Well, green dots just mean that these lines are approaching to you. Like it is exactly like this, but you look from here. You look exactly on it. If you look at the arrow that is approaching you, then definitely you see it as a dot, right? Okay. So it is the line as well, but just the one that looks on onto you. Into you. Okay. So we know this basic reflection law. Let me show it. Here you have some light, then you know that the angle of incidence, like theta I, equals to theta of reflection, right? And some of the light gets refracted, it bends. Here we have another theta, and so on and so on. But this rule could be kept in different kinds of situations. For example, here it would be something like this. These angles would be equal. It would be something like this, maybe. This could be like this, and maybe like this, and so on. This could be different scripts, right? But here in Brewster's law, it would be just one certain script. What is that? At a certain angle, one specific angle, you will see no glares. So polarization, what does polarizers do? For example, if you have polarized glasses, for example, at a certain angle, your vision, would be clear. What does it mean? Your vision would be clear. There would be no glare seen from the water. Yeah, we know that sometimes glares disturb us to see the bottom of the water, even though it is very clear and so on and so on. But the glare disturbs us to see the fishes on the water. However, at a certain angle, there are some angles that no glares are seen because they get completely polarized. As you can see here, this angle of Brewster, then reflection, again, it's the very same law, angle of Brewster. Here it is different angle of refraction, let's call it alpha r. Yeah, as you can see, this thing gets partially polarized. Yeah, if something is approaching like this, here it gets partially polarized. That's not much of a problem. But here, the one that is reflected is completely polarized. As you can see, these lines, they just canceled out. There is, for example, the water is like polarizer right now. It plays the role of polarizer. Okay, so what's the rule for that? These two angles. Yeah, let me choose maybe, I don't know, green or no, let's choose pink. Yeah, these two have to be 90 degrees. That is the most important part. Yeah, okay. In that case, we can write down some formula, for example, which is this one. Yeah, angle of Brewster is this kind of formula. It is arctangents and N2 divided by N1. N2 is definitely, this is our water and this is our air and so on and so on. But let's derive the formula, how we make this formula to appear. Yeah, well, if this is if this is angle of Brewster, this one, if this is a refracted angle and this is 90 degrees, well, we all know that this all side has to be 180, right? Then I would write something like this: angle of Brewster plus angle of reflection plus 90 degrees between them equals 180 degrees. Good. If I move 90 to that side, it would be angle of Brewster plus angle of reflection. It would be 90 degrees. Okay. So if I give some meaning to angle of reflection, then it would be 90 degrees minus Brewster's angle. Okay, so right now we apply Snell's law. Right now we can apply Snell's law, which is N1 sine angle of incidence, but in our case it is angle of Brewster. It is alpha B, and then here we have N2 and sine of refracted angle, yeah, of the light, and refracted angle would be our alpha R, right? Refracted angle. Yeah, I'm sorry. This would be N1 sine alpha B. Here N2, but we know the meaning of alpha R. It is right here, 90 minus alpha Brewster. This thing would be 90 minus Brewster's angle. Okay, we definitely know that sine 90 minus alpha, it gives us cosine. Yeah, then this thing would be N1 sine Brewster's angle. This would be N2. Yeah, this plays the role of our alpha. That's why this thing would be what? Cosine Brewster's angle. Well, right now I can move this cosine to that side. I can move N1 to that side, and then you definitely can see it. Where we got that formula from. This thing would be sine alpha Brewster divided by cosine alpha Brewster. This thing would be N2 divided by N1, and this is definitely tangent alpha Brewster. This is N2 divided by N1, and to find the angle itself, it is equal to arctangents N2 divided by N1, and that's how we get that formula, which is right here. Okay, the last thing where we use the Brewster's angle in our daily life. Sometimes we have some glasses at a certain angle, they polarize all the glares, so we see no any glares. We also have laptops at a certain angle, we stop to see the glares that come out of the screen, yeah, because the light might reflect off the screen and reach our eyes, and at a certain angle, that is the Brewster's angle, all the glares just annihilate. The same thing goes for camera lenses. Yeah, camera lenses can polarize light, so taking out all the glares to make the image better. Okay, so that was it for today. I hope you understand that you understood all of this topic. But if you did not, of course, please write me privately, and I will try to do the best thing that I can. Okay, thanks for your attention. Goodbye.